Okay, in this video, we're going to answer the question, why can't X-ray fluorescence detect certain phases or compounds of solids? It can only give you chemical information in the form of percent mass of certain chemicals. In the last video, we looked at this XRF information that comes off of an energy dispersive spectrometer, and you could see here the different peaks, and we looked at copper in particular, and we went through showing where those peaks come from, starting with the copper atoms that are in a larger chunk of copper. And we came to this idea that the X-rays, the characteristic X-rays, come from transitions inside the actual, in a single atom at a near the transitions that are taking place near the core of the nucleus. So they're at a level that's more like this, I guess, if you were thinking of the atom as kind of a sphere. And these transitions come from replacing an empty electron seat caused by ionization at the K shell. So some form of energy, a photon or a high energy electron, knocks an electron out of the K shell and leaves an empty electron seat that's replaced by an electron dropping its energy and giving off an X-ray as it drops that, or as it gets rid of that energy to fall into that lower level, either from the next shell or the two shells away. So you get K alpha or K beta emission in this case. Now, where is this happening? Well, it's happening near the core, as we said, near the core of the atom. And notice that the core of the atom doesn't really, we will say, detect the presence of these other atoms that are surrounding it. So in our chemistry model, this is similar to this idea where if you have an isolated, in this case we have helium, an isolated helium atom, and another isolated one, they would not notice each other's energy levels, and you'd get the discrete 1s level and 1s level. Here's energy on this axis. Now, if you were to bring these in close enough, these levels would start to notice the presence of one another, or you would say the electrons would notice the presence of one another. By the way, this is just a story that I'm telling, and it's a very convincing story. It seems to be repeatable in terms of measurements. And what happens is this discrete single level of the individual atom becomes split into two levels that they both have access to. So they sort of both feel the presence of these bonding orbitals, and then the star are anti-bonding level. So the star is there to indicate it's sort of an excited level because you need actually more energy to go up into that level. So when we look at, let's see, multiple levels, let's say fluorine atom, we have, when these orbitals come together and they notice the presence of one another, they begin to split into these bonding orbitals and then an anti-bonding orbital. And what we mean by this sort of is that there is an energy state that the electrons, we'll say electrons as waves, could occupy, like a standing wave, at a higher state and a standing wave at a lower state. You might think of these inside of, let's say if you had a string, you pluck the string, this is the low frequency resonance or the large wavelength. This is the high frequency resonance of the standing waves or the short wavelength. So these are starred because they're excited states. So these are the lower energy states. So the lower energy states are the states that are between the atoms and keep them together. And these are what's called anti-bonding states. Well, how is it that that this plays out inside of a solid where you have a whole bunch of atoms beginning to feel the presence of the other atoms? Well, you end up with something a little bit like this, where these once discrete states begin to create a whole series of different energy states that are possible that are separated by a very small amount of energy, like maybe 0.001 or yeah, 0.001 or zero point zero 0.01 electron volts, just a very small amount, um, creating a kind of band, a continuous band of energy states. And you could see that at different lattice spacing, those states are going to split differently, so that at some point it may look like you have a set of continuous states and then a gap and then another set of continuous states. And that's often what you see when we draw these simplified pictures of valence band and conduction band. Well, you can imagine that at different levels that the overlap would be different, and then for the atoms that were, or for the shells that were much closer to the core, you would have to get these atoms much closer to each other until those levels began to split. So what we see in kind of the um, copper, the large atom, is that the outer shells, the orbitals, start to overlap and form these bands at a much larger distance than, let's say, the 2p or the lower one, or the 2s or the 1s would begin to feel one another. So these levels, at the distance of separation that you have, for example, the natural separation between the atoms. In this case, this shows an internuclear separation of like 0.4 nanometers. The 2p level is still a discrete energy level, whereas the 3s, the 3p, and so on begin to overlap. Now, if we were to look at the 2s, that would also be a discrete level down here, as would be the 1s level. So when we consider pictures like this, you see these bands overlapping. These bands for metal really represent a fairly uh, high energy level for the electrons. So the electrons on the outside, the valence, we'll say the valence electrons that feel that are intersecting with the adjacent atoms and feel the presence of those other atoms. Whereas at these lower, if we were to look at the lower levels, we would see these discrete energy, these energy levels down here, as they would be in the absence of any other atom. So if they were an isolated atom. I hope I'm making sense. Okay, so the reason why we can't detect phases or compounds is that if you look at phases, for example, in the iron carbon phase diagram, you know that you could take austenite and you could cool it very slowly, and it will separate into these two different phases, ferrite and cementite. Or you could quench it and create martensite. Now, in the end, you still have the same amount of carbon and iron together, and by XRF, you can't differentiate the two different structures, because the difference in these structures is caused by the different the different phases crystal structure, not by different chemistry. And so the XRF only gives you information at the level of the core electron transitions, regardless of what the crystal structure is.